So the final exam will consist of two parts, a take-home part and an in-class part. You'll have about 1 week to work on the take-home portion. And on the take-home portion, you can work with other students in this class to answer those questions. If you discuss any part of the take-home portion with another student, that means you are working in a group, therefore you must turn in one set of solutions with the names of all the people in your group. George?
When are the labs due?
Well, today in lab you'll have again another opportunity to complete all those labs you need to finish. So this is the third lab period, which means 9 hours in lab. So I'm hoping you'll finish it today. And then the in-class portion of the final exam will be 3 pages long. It'll be held on Tuesday, May 29th from 8 to 11. It'll be open book and open notes. It'll be the same length as a midterm exam, so I'm hoping it won't take you more than an hour and a half to complete the in-class portion of the final exam. The in-class portion of the final exam is to be done individually. That is not a group exam. If you are concerned about your grade, all I can say is if you've turned in every assignment in Chem 1B, if you get an A in the final, then you get an A in the class. Now, as all of you know, since you're going to be scientists and engineers and health professionals, there are patterns and trends in science and engineering. So, for example, if a student has been getting C's the entire semester, don't think all of a sudden it's going to be Shangri-La on the final exam and you'll all of a sudden get an A. I hate to disappoint you, but that's how it is. On the other hand, if you've been doing well the entire semester, then I expect you to do well on the final exam. I'll be very disappointed if you do well on the final exam. Okay, although I should say there are exceptions to the rule. There was one time when a student in Chem 1A, I think he had been earning C's in every assignment, and all of a sudden Chem 1B finally got an A. I was thinking, wow, whatever happened must turn the course. So we did Chem 1B, and guess what grade this student earned in Chem 1B? A C. So there was an outlier, and I'm not quite sure what happened. So that student got an A on that final exam. Ever since then, I've been suspicious about what happened. I learned in my memory that the student did well, really well on the final exam. Then, you know, it was like, it's like you know, a runner who can run an 8-minute mile. All of a sudden, he runs a 4-minute mile. That doesn't happen, does it, Omar?
Oh, no.
No, it doesn't happen.
It's not possible.
Yeah, so that's why that's significant. It's not going to happen. Okay, so let's continue our discussion of nuclear chemistry. So radon is an external radiation source. Now, let's go back a few slides and look at this slide here, because we were looking at different sources of radiation. So note that natural background radiation contributes 130 milligrams per year. This is the most, at least on this table, radiation sources. Okay, then we talked on Tuesday about potassium-40 being an internal radiation source. Note that carbon-14 is another internal radiation source. Note that the difference between carbon-14 and potassium-40 is that the half-life is different, and then the isotopic abundance of each isotope is also different. Okay, so that's going to affect the amount of radiation from each source. So let's take a look at external source, radon. Now let's answer this question first. Where does radon come from? Yeah, so radon comes from the ground. And actually, let's take a look at this radioactive casing. This is on the next slide. So radon has a symbol Rn, so this is radon. So note that radon actually comes from uranium-238. So uranium-238 is the most abundant isotope of uranium, and that is found in various minerals on Earth. So note that uranium-238 is an alpha emitter. It has a half-life of 4.46 billion years. So that means that if the Earth is 5 billion years old, note that half of the original amount of uranium on Earth is still present. So philosophically, I'm not quite sure what that means, but at least it's an interesting statistical fact. Okay, so anyway, let's do this. Just for practice, write a balanced nuclear equation which shows the alpha decay of uranium-238. Okay, so once you have your balanced nuclear reaction, show your reaction to the person next to you. See if you get the same reaction. Okay, so would someone like to come to the chalkboard to show their balanced nuclear equation for uranium?
First time this semester. Got good at least once.
Oh, good.
Yeah,
enough though, right? Am I? Missing a letter. Where? Letter. Oh.
Okay, so what do you think of Joseph's
Is that the
nuclear reaction?
where?
Thumbs up or thumbs down? Okay, good. Okay, so note that when uranium-238 undergoes alpha decay, thorium-234 is produced. So that's also shown on this table. So that's the decay products. Note that thorium-234 undergoes beta decay with a half-life of 24 days to produce protactinium-234, and then protactinium produces uranium-234, which produces thorium-230, which produces radium-226, and then radium-226 undergoes alpha decay to produce radon-222. So what I would like you to do is to write the balanced nuclear equation, which shows the radioactive decay of radium-226 to radon-222, and then we'll talk about radon. Yeah, I'm not sure if any of you are old enough, but there was a TV series called Room 222.
Okay,
Way back
like
It was a series about education.
seriously, I got a question.
You got a question?
Yeah, where does the helium come in?
Where did the helium come in? Joseph, answer Mariah's question.
Where did the helium come in?
The what?
The helium.
Oh, because it's an alpha type radiation. So then you have to use the that's the nucleotide symbol. That's where I got it from.
Okay.
Erica.
How do you know when to add and subtract from the 238 to get to 34?
Joseph, answer Erica's question.
Usually subtract it when once the beta particle, then use the electron symbol. If you go back to last Tuesday's lecture, it'll be on the table, and you can use that as a reference.
Does that answer your question? Okay, so again, radium-226 to radium-222. George. Yeah, no, you don't have to worry about the charge. So note that for a nuclear reaction, we don't have to worry about charge conservation. That's only for a chemical reaction. We don't have to worry about a nuclear reaction. Yeah, so that's a good point, because in the chemical reaction, note that those conservation laws, which we held as those tried and true universal laws, are actually not true in a nuclear reaction. So there's no such, that conservation of mass law goes out the window for a nuclear reaction, because we know that when mass is destroyed, what happens? Yep, energy is created.
Let's see.
Okay, so you guys have a balanced nuclear equation for radon to produce radon-222? If you have, show that to the person next to you, see if you get the same answer.
Oh, sorry.